Hello, in this video I would like to introduce you to the concept of statics. What is statics, you ask? Well, statics is the study of forces and their effects on a system in a state of rest or uniform motion. Uniform motion means that it has a constant velocity. So, rest is also uniform motion because when you're at rest, you do have a constant velocity. It's just that your velocity is equal to zero. So each of these pictures show things that are in rest. For example, these boxes over here are static because they have been placed on shelves and on pallets in an orientation where opposing forces are canceling each other out, and they're in a state of equilibrium is another term that you might have heard it called. So this warehouse is static. You don't have boxes falling and tumbling down. This bridge is stable because we have created the beams to act with each other so that opposing forces cancel each other out, and we have a uniform motion or a velocity of zero which keeps this bridge at rest, and that's why when you load it with cars it stays stable and supports the cars because it is static. So in order to talk about statics, we need to understand Newton's three laws of motion. His first law of motion, or the law of inertia, states that an object in a state of rest or uniform motion will continue to be so unless acted upon by another force. This describes the relationship between velocity and forces. So this train will continue to move until something breaks, friction, something in a force applied in the opposite direction changes its uniform motion. Newton's second law of motion describes the relationship between the net force and acceleration. So first law, force and velocity. Second law, force and acceleration. And it says the acceleration of an object is proportional to the net force acting on the object and inversely proportional to the object's mass. You might more commonly have used this in your physical science classes or in your physics classes. It's the formula F equals ma. This brings us to Newton's third law of motion that says for every action there's an equal and opposite reaction. This describes action-reaction pairs. So as this ball hits this ball, it pushes this one out, which causes an equal and opposite reaction back in, which pushes this one back. So that's why these little puzzles that you may have seen that often sit on people's desktops just click back and forth because of Newton's third law. So let's talk about this word equilibrium that I threw out in the introductory slide. Equilibrium is a condition where there are no net external forces acting upon a particle or rigid body, and it remains at rest, or it remains at a constant velocity. And remember, this rest and uniform motion are the same because rest is a uniform motion where velocity is zero. So, this drilling rig is in the ocean because we have balanced out the forces acting on it from the ocean with the forces that we're using to support it so that no net external force has more force acting upon it to push it and crumble it down. So the state in which there are no unbalanced forces is called translational equilibrium. So everything is balanced. So you see this bridge that's static, it's staying here, people can drive on it, nothing bad is going to happen. That's because the sum of the forces in the x direction, or from the left and the right, based on our free body diagram work, is equal to zero. Then in this, and the sum of the forces in the y direction, which we talked about in our free body diagrams, is also equal to zero. So the up and down forces are exactly the same and they're balancing each other out. So this is considered an equilibrium or static, and this is a good bridge. It works for us. When you have more force acting down than you have pushing back up, that's when you could have tragedy or catastrophe in engineering, and you have an unbalanced equation. The sum of the forces in y, in this example, are not equal to zero. We have more force pushing down than we have pushing back up. We are not in equilibrium in this case. We are unbalanced. So this is why equilibrium and statics are so important to us in engineering. It's important to note that we also have rotational equilibrium. So we not only need to consider the sum of the forces in the x and the y directions canceling out, but we also want to make our rotational, as we see here, our rotational forces cancel out. As we see here on this teeter-totter, we want the forces that would cause this to rotate clockwise to counteract or to balance or equal out with the forces that are going to push on this teeter-totter to make it rotate counterclockwise. So that's what we talk about moments, and we're going to review moments here very quickly, but that's the rotational direction. So this says the sum of the moments, and when you see this M for moments, you might think rotation, has to also equal 0. So 3 very important concepts for our lesson in statics. So for example, we just went through this yesterday's videos. Hopefully you realize there are 2 different kinds of quantities we need to worry about. One is scalar, and it's just a physical quantity that has a magnitude only, like the number of students in class. That's magnitude only. Here's some other examples from science, such as mass is a magnitude only. You can't weigh a positive or a negative amount. That's a direction. A length. Time is magnitude only. We don't go back in time or forward in time. I know some of you would like to investigate time travel. Any shout out to all those Doctor Who fans out there. But really, time is a scalar quantity. It has magnitude only. We have only an amount of time, no direction for it. Here's some other examples as well. Then we have vector quantities, which is we looked at yesterday and we have studied today about vector quantities that have both a magnitude and a direction. Things like position. I can be, instead of just saying the length is 12, we could be 12 miles away from home, or probably a better example would be 12 miles east of home or 12 miles west from home. I could be 12 miles on this position. I could be 12 miles to the left, 12 miles to the right. We could also denote that with a positive 12 versus a negative 12. Those denote a position and a magnitude. Velocity, because we could have increasing velocity, then we could have positive velocity versus negative velocity. So that's a vector quantity that has both magnitude and direction. Our forces that we're getting ready to talk about when we talk about statics are vector quantities. Is my force acting in the up direction or the down direction, the left direction or the right direction, as we saw in our free body diagram work? So, what is a force? The force is the pushing or pulling interaction of objects. So a vector quantity is known by its magnitude, its direction, and point of application. And we use these vector quantities and these vectors right here to help us with identifying a force. We use these vectors to show there's a force acting with some sort of magnitude, and that's the length of the vector. It also acts in a certain direction, and so you see the arrow that shows, and this 21.8 degrees northeast is telling me what direction my vector is acting in. And then at the point of application, which in this case is the origin. Forces always occur in pairs, and especially for our statics, we want to have pairs because we need them to cancel each other out. Now, they don't always have to come in even pairs, but when we have static equilibrium, I guess I should say, they're always going to occur in pairs. They will always act in opposite directions, and they will have the same magnitude, because that's what makes them in equilibrium. The amount I'm pushing down is the same as I'm pushing up, and that's why nothing is moving. The amount I push to the right is the same as the amount I push to the left. That's why nothing is moving. And then for moments, let's not forget moments. For the rotational, the amount that's causing it to rotate clockwise, we have the same amount rotating counterclockwise, and that's why you don't see any rotation. So for our free body diagrams, we've talked about this, so I'm going to click through it quickly because we have done some work on this. every object exists surrounded by other objects. So perhaps resting against something, moving through its surroundings. So while an object is in a given environment, it interacts with other objects, exerting forces on those objects. As we're going to see when we do the trusses, this is what we're working up to, is trusses. The free body diagram isolates that object from its environment. So instead of seeing the environment and everything, we're going to take it out and examine it and all the forces acting upon it symbolically, one piece at a time. This allows engineers to focus on the forces acting upon the object. From the free body diagram, engineers develop equations which can describe equilibrium, motion, momentum, strength, and many other physical properties. So we talked about force being a straight line, push or pull, and we're going to use it with these vectors, these arrows, so showing a force acting up. This arrow will show a force acting to the right, but it's also important to know that it can also be acting at a diagonal amount, and that we have direction. That's where this angle helps us. So this direction is up, this direction is right, this direction is some angle from the horizontal, and it also has magnitude. Magnitude is illustrated by the length. So if you have a force that is more than another force, then when you draw its vector, you should draw it longer than the other vectors. You should have done your force component work previous to viewing this video, so I'm going to glance over this pretty quickly so I can keep this video short. A single force can be replaced by component forces if their combination produces the same effect. So I could draw this diagonal force acting, say that I'm pulling on a sled in this direction. I can break it down into the amount that I'm pulling in the x direction and the amount that I'm pulling in the y direction. As long as, if I put this y direction vector right here, it gives me the same result. If I go this way in the x direction, this way in the y direction, I end up at the same point as I would if I traveled straight in this distance. Let's look at free body diagram components for moments, because we did not talk about this in our free body diagram work earlier. Remember that a moment is the twisting effort about a point or axis when a force is applied at a distance. So we denote this on our free body diagrams with an arc and an arrowhead that shows if it's turning clockwise or if it's turning counterclockwise. And sometimes you'll see them denote the CW just to show that I know it's clockwise. CCW stands for counterclockwise. So moment is the amount of work that you have whenever you do a twisting or a rotation. And so remember that work is a force times a distance. So we're still just doing force times distance, but we call it a moment so we realize that we're doing a rotation or a twisting. Now when you're doing this, so for this example we're having a moment whenever we have a wrench that's trying to tighten or loosen this bolt. The distance that we use for our distance calculation, so I would need to know to find this moment, the amount of force I'm applying, and then I want the distance to be the moment arm, which is referring to the perpendicular distance to the line between the object and the force. So here's my object, here's my force, here's my perpendicular distance. So the length of the handle would be the distance that I would put in for my moment arm. So that's an introduction to some of the topics we need in order of learning about statics. I hope that this has piqued your curiosity. The next lesson in this, we're going to go further into this idea of moments, and we're going to start doing some equilibrium problems, just looking at moments and trying to figure out how our moments cancel out so that we have beams that stay in equilibrium. Thank you for listening today, and please go to Blackboard and follow your announcement for the rest of your assignment.